All right, hello everybody. Welcome back to episode 31 of Coding Until I Get an Embedded Internship. Usually I look at the date like at the bottom right and I just figure out the episode, but now since it's June I can't do that anymore, which is kind of sad, but it's good. We've made a lot of progress so far and I feel like I've learned a lot this month. Just improved my C fundamentals. Also learned a lot about microcontroller stuff. So that's good. Today I want to work on... what do I need to work on? Let's see here. So let me pull this up. Okay, so let's pull... Okay, right here. So, what do we got to do? So we got... Oh my god, I downloaded this. So we got RTOS... Sorry, microcontrollers. So we got GPIO, ADC/DAC, timers and counters, PWM, watchdog, interrupts, DMA, and clock management. Today... Last time we were just briefly learning about USB stuff. I think I can do that on my own time. I don't think... and we'll probably learn this in school anyway, so that's, yeah. And then as for this stuff, today let's cover DMA and clock management. Let's look at the resources. Introduction to direct memory. Okay, let's watch this video real quick.
You've been following along with our discussion about interrupts. Well, you know that interrupts improve the performance of I/O by not requiring the processor to keep checking if I/O has something to say. We can make it even better.
Oh. Before I even go on, does ESP32 have DMA? Okay, so ESP32 does have the SPI DMA driver normally handles all the DMA stuff for you. All you need to do is make sure it's in a DMA channel. Okay.
We talked about interfacing memory to the bus. And so we had some sort of a group of wires, right? And there were three groups of wires. There was address that allowed us to identify which memory location we were trying to communicate with. And there were data lines that allowed us to pass the actual data back and forth between memory and the CPU. And then there were control lines which controlled that process. And so we had the CPU that was communicating with memory, right? But beyond that, we also had I/O connected to this bus. All right, input and output. And that was really when we started our discussion with communicating with I/O. Now, remember that polled I/O meant the CPU set up the I/O and then had to keep checking back with I/O to see if it had something to say. We removed that responsibility by saying, okay, CPU is going to set up the I/O device. And then the I/O device is going to have enough intelligence to perform its operations and then alert the CPU through an interrupt to say, hey, I got something to say, or I'm available for whatever process that you needed. All right? The problem is it doesn't quite solve all of our problems. Because let's say that we've got a large block of data, maybe one of these I/O devices, maybe it's a network interface card, or a hard disk, or a solid state drive, something that its job is to grab a large amount of data and then have that large amount of data move from the device into memory so that the CPU can operate on it. Okay? So that means that the interrupt service routine ends up being something like this. Well, it's a large data transfer. And how do you do a data transfer? Well, let me go down to the assembly language level. I realize that this is not an assembly language class, but to get an idea of what the CPU is doing, let's take a look at some of the assembly language commands. So we have LDA, R0, and then R1 in brackets. Let me explain what this instruction is doing. The register name, so these two are registers. Remember the top of the memory hierarchy. These two are registers. Now the one that's in brackets means that instead of using a piece of data in that, we're treating that as an address. And so R1 contains the address that we're reading from, we're loading from. And so maybe if we're receiving a large message from a network interface card, it's pointing to the address of the network interface card's buffer that allows us to bring in that data. So it's pointing to the address inside of the I/O device. And then R0 is bringing that data into the CPU. So we've got to read from I/O into the CPU. Now, the second step is to take the data that we just read and store it. So we're going to store R0 to what R2 is pointing to. All right? Now, R2 is probably pointing to an address in memory. So we've got one read into the CPU and then a write from the CPU. Now, this has got a couple of problems. Problem number one, each data transfer or each data element transfer requires 2 memory cycles. All right? So, I've got one data element. How many times did I have to access the bus in order to move that one data element? I had to do it twice, a read and a write. All right? So that's one problem. Now the second problem, though, is that it monopolizes.
Requires 2 memory
CPU.
cycles.
So during this data transfer, the CPU is having to do rather trivial operations. I mean, these are not high-end floating point multiplications or anything processing. We're just moving data. Wouldn't it be cool if we could get something else to handle that transfer for us? Well, it turns out that we do. We can create a fairly simple processor referred to as a DMA, or a controller. And DMA stands for Direct Memory Access. So we've got this little processor, and it doesn't need to be all that complicated. I mean, think about it. To do this transfer, I needed 3 registers. I needed one register to show the address of where I'm reading from, one register to contain the address of where I'm writing to, and one register to contain the data. That's it. Right? Now, what happens is that the CPU will tell the DMA, here are the details of the process. I need you to read from this I/O device to memory. Or maybe we're sending a message through a network interface card. So the CPU might say, I am going to ask the DMA to write this block of memory into this I/O device. Now, notice, we've got a problem. There's now 2 processors trying to work on this bus. They can't both be using the bus at exactly the same time. So the CPU has to stay off the bus long enough for the DMA to do that transfer. We're going to talk about some of the ways we can solve this problem, but let's take a step first. Let's see what the DMA has solved so far. So far, it's solved the problem of the step 2, monopolizing the CPU. Let's see if we can't figure out how to solve the problem of step 1. Now, it's pretty simple hardware. It's a pretty simple processor that's going to allow us to do this transfer. But what does the CPU need to do in order to get the DMA to do its job? So, to control the DMA, the processor must, or the CPU must, first of all, we've got to tell it whether it's a read or write operation. words, what direction are we going? Are we going from memory to the I/O device, or are we going from the I/O device to memory? We're going back to something simple like some sort of a storage device, like a hard drive or a solid state drive. If I'm storing a file, you have to tell the processor that we're writing to I/O. If the storage device has read a file and it wants to be brought into memory, we need to tell the DMA that that's the direction that it's going. All right. We need to tell it the address of the I/O device, right? So, and once again, this I/O device itself, it may just have a specific single address that it's going to be passing everything back and forth to, or it may have a block of addresses, and we know whether we're incrementing through that block to bring it into memory, or if maybe we're just reading that same memory location and making multiple reads to be stored into memory. All right. Then we also need the address, and by the way, both of these addresses are going to be starting addresses, the initial address, where we're going to start this block transfer of data. So, of memory that we're accessing, all right? And then the last thing is the size of the block to transfer. Those four things are enough to get the DMA started. All right, now that doesn't take much of a complicated processor, but it does mean that the DMA is going to need to monopolize the bus. I mean, think about it this way. If I've got the CPU reading from memory in order to execute code while the DMA is doing a transfer, those address and data lines are going to be, well, they're going to have contention. It's called bus contention, where these, we've got two different things trying to drive the line or access the lines at the same time. That's a problem. So what the processor does is it allows the DMA, it backs off in order to allow the DMA to access the bus. That's called cycle stealing. Let's talk a little bit about that next. So, what does the DMA need to do in order to get the CPU to let it use the bus? Because the CPU really should be in control of the bus.
Instruction for CPU for the processor. That's pretty good. So and then the solution would then be to use direct memory access. And be the one to allow read or write.
The bus.
Request the bus.
From the CPU. All right? Some sort of a thing called hold request. There's a number of different names for it depending on the hardware you're using. But a request from the DMA to say, I need the bus. Now, the CPU then acknowledges the request. It does this by doing something called tri-stating the bus. All right. Now, what does it mean to tri-state a bus? Well, in Boolean, we haven't talked much about tri-stating, but in Boolean, how many levels do you have? 2, right? 0 or 1. A third state means that it kind of disconnects it. Usually this is represented by a Z, the letter Z. And in electrical engineering type or electronics type nomenclature, the Z means high impedance. It's like
yes.
It just basically means I am disconnecting myself from the circuit. So that's the third state.
High Z, yeah.
Try, right? And so the CPU acknowledges it by saying, okay, I'm going to give you a signal saying, I've acknowledged that you can have the bus, but I'm also disconnecting myself from the bus, all right? And then the DMA takes the bus to transfer the data. Or more specifically, the data element. Now, this is not an interrupt. We're not calling any sort of interrupt service routine. The DMA does this request. It's done through hardware. The CPU is not changing its mode. It's not changing the code it's executing. It's not stopping the code it's executing. It's just simply a hardware thing that allows us to go through this process to allow the DMA to have access. And then the DMA releases the bus and the CPU can take control of the bus. Now, this does slow the CPU's processes down, but we have kind of something we've already talked about that allows the CPU to execute code while the DMA has seized the bus or is stealing the bus. If you remember, at the very top of the memory hierarchy, we have registers. But right below the registers, we also had the RAM cache.
Okay.
All right, so we have the CPU. Now, the CPU actually is executing out of its cache, not directly out of memory. And if you go back to episode, I don't know, when we were talking about the caches,
memory.
you recognize that the CPU makes a request to the cache. And the cache makes, if it does not have the element, either instruction or piece of data that the CPU is looking for, it makes a request to memory and a block is brought in. All right? So, during this period of time, while the DMA is stealing cycles from the CPU is not necessarily stalled. It probably is executing code still just fine out of its cache. All right? It means that we really are only slightly, if for example, we do have a cache miss, which meant the CPU requested something from the cache that wasn't there, if the DMA has taken control of the bus whenever there's a cache miss, yes, we are going to have to stall the process on the CPU to wait for accessing it, to wait to access memory. But for the most part, we should be executing out of our cache, which means cycle stealing shouldn't have that great an effect. Now, we've talked about solving the second problem. The second problem was the fact that the data transfer, which is a really simple operation, was really monopolizing the CPU, taking time that the CPU could be doing more important things. But what about that first problem? The first problem, where we are accessing the bus twice. Well, let's see if we can't solve that one too. Now, one of the ways to solve the problem of accessing the bus twice, let's solve that one. Now, one of the ways to solve the problem of accessing the bus twice for every single data element we're moving, well, could be to purchase I/O devices, such as a hard drive or a solid state drive, that actually include their own DMA. And by doing this, what we've got is the ability to have the DMA do a transfer back and forth, reading and writing to its I/O device through its own bus, through its own very close interface. And then the communication with the memory just takes a single bus cycle. And so whenever we're doing a block transfer, in this case, when the DMA is associated with its own I/O device, then what happens is we have a single bus cycle used for each data element that we're transferring. Now we actually have another solution that could be done. By doing an interface through a DMA, instead of going to a single I/O device like a hard drive or a network interface card or something, instead connect it to an I/O bus and then have all of your I/O devices hanging directly off of that bus. And so in the case of having simpler I/O devices, we could just simply have a bus. For example, maybe a USB, maybe a USB hub, or some sort of another type of network interface. What you can have is all of your I/O devices hanging off a separate bus that the DMA communicates with. This would allow us to have a single memory cycle stolen for every single data element that we're transferring either to memory or from memory. All right? Now, this is all cool in terms of transferring large blocks of data, but it turns out that DMAs are also used for some rather unique applications.
DMA request the bus. DMA will does it in one instruction.
For example, picture this. Maybe I have an array of LEDs. All right?
Array.
Yes. So I have, a small matrix of LEDs. And I want to send a pattern. I want to make this pattern that the LEDs go through. Maybe it's one of those little personal devices that has a ring of colored LEDs. And what I want to do is I want to send a pattern so it'll make a swirl in one direction or a swirl in another direction, or maybe they'll all dim and all get brighter. Well, what I can do is I can create in memory an array of values. The things that are going to set our LEDs to different patterns of ones and zeros. It's a problem of monopolizing the CPU, and cuts through the array. Read through the array of each one of these different data elements that I'm sending to those forever. And this will include their own DMA, solid state. It's I/O devices, such as a hard drive or a solid state. This I/O device, data element we're moving, well, could be to purchase I/O devices, such as a hard drive or a solid state drive, that actually include their own DMA.
Oh, okay. Alright, I gotta use. I'll be right back. Alright, I'm back. Okay, so let's get to work. I'm gonna try to configure the DMA on the. This is a good channel. So let me save this. Actually, I think this is a very good channel.
State by the heart or purposes. It tells us the source, what to start looking at. We need to put things of single instruction set up. So whatever parameters need to be, means that that particular file time.
Okay. This is a very good channel.
Without input components to it. So coming out of the processor, you have a microprocessor here. You have a bidirectional set of wires, both directions going into and out of the processor, that carried data. And then in order to point to a specific address that the data was contained at, we also had a set of wires coming out of the processor that contained address. And then we also had a set of wires coming out of the processor, should have made my processor a little bigger here, that provided control. Now, the control, that view bar right on the address lines, and that 8 lines to control the same time. Now, it's been a very with like an embedded.
Yeah, I should probably. Okay, so let's begin. Okay. So I want to get how does DMA work on ESP32? DMA, let's search that up. Have more requirements. Okay, so this is more. This has to do with SPI. There's a good video on this. Let's go over that. Skip. Okay.
To another video on ESP-IDF. Today's topic is the I2C protocol. We'll cover
I2C, I squared C. Is there any video? Does this guy do any video with SPI? Nah, he only uses I squared C. Oh. Okay. There are no flash memory. Onboard I squared C sensors.
Welcome back to another video calls with the others be to start using I sensor running on 3.3 volts and address temperature data register which you file P180
Okay. Nah. Okay. This is. Oh my god, this makes sense. It's starting to make sense. Okay. In my professional projects, it goes like this sensor is only I squared C, so I squared C it is. This sensor has both I squared and SPI, so my microcontroller has two I squared C and one SPI, so one I squared C is. The rule of thumb is that one normally uses that. The one normally uses the I squared more devices. SPI is faster than UR is for more complicated devices. That's for UR, but again, I am. Okay. And this is a good comment. I hope it's correct. Let me save that as well. Wonders why battery. So that's like that's like the general idea.
Grammarly.
Oh. And I think that is the answer. Like, it just depends, right? I mean, you have a microcontroller, you have the SPI or whatever. Shoot. Oh god. Oh, my microphone. Super weird. Anyway, let's try to... I want to see... SPI on ESP32. Ah, okay. Polling DRAM. Miso is SPI 2 GPIO number. Okay. Shit. The serial. No. Okay, let's begin. I have so many files included here. It's crazy. Okay. So we have the SPI interface. Let's get that started. Let's configure. Shoot. Oh, what the frick? What? No. The definition. Yo, what the fuck? Unions. My beloved unions. GPI open. So Mossy. What's the Mossy IO number? Miso. Oh, I don't know. Let's just put like random numbers for now. S clock. Wait, S clock. Wait, what? Is it S clock? Yeah, it's S clock. Sorry, S clock 20. And then dot max transfer size equals how much bytes are being sent. What is the quad WP? What's that? Let's see. Write protect signal. Mossy. Miso. S clock. Oh, it's sorry. Used for 4-bit QIO/QOut transactions. Also for the data to signal in the octal/. Okay, so I don't think we need to do that right now. -1. So dot quad -1 and then dot quad. Let's do that. Anything else I missed here? I don't think so. Okay. We can change this if we want. So let me finish up the struct. And then let's configure the SPI bus initial. What is... Let me go my document real quick. Okay, so I had a little bit of a grand realization the other day. This whole process of configuring it is literally just the equivalent of us in like raw C, like volatile C, I guess. This is just the equivalent of us just using the memory map, just putting bits into memory map registers. So that's pretty neat to know, and it makes sense because it's a struct, right? It's very similar to a struct. Okay, so that's cool. Those. So let's put the host ID, a timer, DMA. Oh, right here, the SPI DMA channel, right here, the SPI DMA channel. What is the host ID here? Okay, that's really cool. Okay. So apparently, let me double check this with the documentation. So SPI 1. SPI 1. SPI 1 is not a GP general purpose SPI. SPI master driver also supports SPI 1, but quite a few limitations. See notes on using SPI master driver on the SPI 1 bus. Okay. To use SPI master driver on the SPI 1 bus, you have to take care of two problems. The code and data should be in the internal memory when the driver is operating on the SPI 1 bus. The code and data should be in the internal memory. Okay, so there's like a... Yeah, okay, so can't access PS RAM or flash memory, which is a big limitation for SPI 1. Okay, according to the documentation. So we have to use the HSPI or VSPI host. SPI host, SPI 2, SPI 2. Okay, that's good. Now let's put in the address of bus configure. And what DMA channel? Let's use one. Well, how many DMA channels are there? Okay, so the enumerator SPI DMA channel 1. So this is how okay, perfect. So this is how you enable the thing. Okay, let's do that. Perfect. Now let's do attach a spine. I'm gonna have to use Wi-Fi one more time. We'll be right back. All right, we're back. So let's do that. Okay. $13. Okay. There's still okay. The IO mux pins are given, right? The matrix. Oh, okay. So you can use the matrix as well. That's pretty cool. Mossy, so but let's just set it to 13. Miso. What about miso? So it'll automatically remap if even one of the pins is correct. Well, miso. Miso is 19. Miso is 12 for SPI 2. Miso is 12. What about S clock? S clock. Pin 13, 12, 14. Okay, good. So that's going to be our... Okay, that's on the right side of the ESP, which is good. Now let's cover the next part, which is we need to attach the device on the SPI bus. Okay. Wait, let me connect this. Hold on. Let me connect this SPI. Good stuff. Okay. Okay, so what do we need? Okay, let me just look at the definition here. The default amount of bits in command phase. Bits in the address phase. Like, there's a lot of stuff here, but do we need all of this? Let's do clock speed in hertz. What do we do here? I don't know. Okay, mode equals 0. Because I think that's just the... Yeah. This is like... SPI device half duplex. Why would you use a half duplex? What? It's full. Chip select. Okay, chip select. It's active low. Chip select is active low. So SPI can both full and half duplex. Oh god. This is good stuff. I don't know. Some big number. While true, this is very. I wish. Damn, I don't know what's happening. Like, I think this is best used for like having an actual SPI device and not like just trying to communicate with between the IOs, but okay, SPI bus. Compare TX and RX data. Compare TX and RX data. Now I'm going to my three, four, and
'Now that I use Monday
Oh
started.
my god, stop. Watch a video.
You are doing great. Once again, you are most welcome in my YouTube channel White Loop Robotic and Automation. Today we are going to learn how to develop SPI driver as a master mode for ESP32 using SPIDF and embedded C. So let us get started step by step. This is previous project. Now I will create here new project. Go to ESP IDF extension and click on new project wizard. Okay, and as
Okay.
pin number and now chip select pin. Okay, clear handle SPI handle SPI underscore device.
Also, I think
underscore T. This is handle. Now going to configure SPI. So we have to declare and define SPI config structure. So
yeah. Also, yeah. I think it's probably also good practice to. Yeah, let's just do this. So 12, just for the sake of good practice. S clock. S clock is 15 in this guy's case, which is kind of weird. Why is S clock 15? S clock should be 14. Okay, I'll just change it later then. But for now, let me just do 14.
SPI bus config. Okay.
Mossy.
And it is
Miso. S clock.
SPI config. Okay, I would pick going.
Okay, so this guy he does it like okay, so it's a big number but just not this big. So how many zeros? Okay.
128 for 50% duty cycle. Okay, now configure the mode. Queue size is 1.
Okay.
So I will tell you what is queue size. Okay, we will see step by step. Queue size means transaction queue size. This is what
Okay.
is queue size. Okay, we will see step by step. Queue size means transaction queue size. This sets how many transactions can be in the air. Okay, realize to press up. Let me try to grow na bus device
It's gonna have to.
and pass here host SPI to host because of we are using SPI 2 and SPI config address big add by size define with 0
Okay. They're just doing the same thing as me.
variable. Okay, printf
Okay.
I will pass this variable sendBuff its size okay string what we want to send. Hi, I am from ESP32. Okay,
Oh, it gives the pointer.
we have to set its length.
Do you have the receive buffer? Address of T 0.
T dot length is size of sendBuff into 8. It is in bit, that's why we are multiplying with 8. Okay, T dot this is sendBuff. T dot RX buffer. It is receive buffer. Okay. Now I will call it transmit function. SPI device transmit and I will pass here handle comma address of T. Okay. Now I will print transmitted buffer. So printf transmitted percent as new line. Okay, this is sendBuff. Okay, and now I will print receive buffer. Okay, printf I will use under period underscore okay. So now code is ready. Sorry, you can see in video. I have sorted Miso and Mosi bin. So whatever I will send from Mosi, then it will be get back on Miso. Okay. So whatever I will send, it will print on received buffer. Okay. So first of all, I will build this code.
Okay.
And another thing is okay. Here we have to pass SPI device config. Okay. And now everything is correct. I think pass SPI device config. Okay. DMA CH auto. Okay.
We also have to process this. No, we're good. What is this asking for? It's a SPI device handle T. What? Okay. What is this? Oh, you don't need the address. You can just put the. It's not a pointer. Okay. Oh. Oh. Okay.
And flashing. It is printing hi, I am from ESP32. Transmitted is hi, I am from ESP32, and received buffer is same. Hi, I am from ESP32. If I will remove this jumper wire, then receive buffer will be not printed. Okay. See, receive buffer is empty. There is no receive buffer. It means it is not receiving any buffer. If again I will connect. Okay. And press reset button. Okay. Hmm. You can see it is printing. So friends, I hope you enjoyed.
Okay, I see. So quick question. So DMA channel 1. What does auto do? Auto is 3. So automatically selected by the driver. Okay, I see. All right, I'll be right back. Let me do something. Actually, I'll take a quick break right now. So like 10 minutes. I'm back. All right, guys, I'm back. So, today, okay. So yeah, we worked on SPI. So let's understand this. Let's get the MASI, the MISO, the clock. Okay. So for those who don't know, MASI stands for Master Output Slave Input, and MISO stands for Master Input Slave Output. So yeah, so this is just the master outputting stuff into the slave, and then the slave outputting stuff to the master. Simple as that, right? We configure the host device. Configure the host. Shoot. Okay. Oh, okay. So in this instance, the slave, there is no slave in this instance. It's technically there is no slave. Otherwise, we'd have an external device, like for example, a sensor, right? But in this case, if I connect the GPIO pin 13 and 40, so if I connect the MISO and the MASI together, it sort of acts like a feedback loop in a way, mimicking a slave. So that's what it's about, right? Okay, so SPI handle. So this is, we create the SPI handle. So the host is so we create the SPI bus. So this is like, the bus is like the actual wire connecting between the master and the slave. And the DMA channel. So DMA. Let me start set this up. Okay. SPI handle. So the handle. The task, okay. Device, so you add the device. So the clock speed is 1 megahertz, right? 1 megahertz. And then so duty cycle 128. What is the duty cycle? I don't know. Chip select queue size 1. Okay, so we only allow 1. SPI transaction. What does this do? Okay, this just okay. I think I'm pretty sure I know what this does. Okay. What the frick? What a definition. That's a buffer. So it returns number of characters. Is this code like... Wait, hold on. Yeah. Oh my god. Holy shit. My microphone. that gave me a heart attack for a moment. I was like, wow. That Sorry about that. Okay. So you can do both. I was like, why is this guy doing this? Why can't you just literally just write in the string? Okay, you can do both. It's not that big of a deal. Then you do this. Okay. TX buffer. There's TX buffer. RX buffer. And you transmit the information. Okay. One thing I'm noticing in a lot of the code is that they use unsigned integers a lot. So yeah. Why? Okay. And next question, let me ask Google. Why is yeah, no, what is why does SPI not use it? So that's initialization and setting up the hardware software. Okay. Configuration and then adding the device. Configuring the device and we're adding the device. Okay. Okay. All right, that's good. Now, map set. That's how ESP32 works, right? Sorry, SPI works. ESP32 SPI works. So you configure. First, you need to configure the bus. This is the actual wire. Then you need to initialize the configuration. So you have you get the host ready. You get the configuration, and you set the DMA channel in this instance. And then you add the device. You configure the device. Okay, good. Miso and a mossy. A miso and a mossy. Okay. So next. Right, so that's good. But we also came here for a DMA. Like, why do we need DMA in this instance? Like the SPI DMA channel. Let's use the stack and the heap. Okay, hold on. So let's consider allocate. So we allocate is stack memory. PS RAM افتتاح. Oh, okay, so apparently you're supposed to do something. You're supposed to do add the keyword word aligned at ATTR, word aligned ATTR. But then there's a problem. Because I did it. What does this do? Apparently it's supposed to force the data to be 4 bytes aligned. Or the buffer will Oh, word aligned. Oh my god. Yes. I remember this. The addresses need to be aligned. Okay. So like what is the Okay, let me read this. You can apparently you could either do that. You could either do that. You can word align it. You can forcefully word align it. So this ensures that a buffer is 4 byte aligned. Okay, so this ensures that it's 4 bytes aligned, Buffers are an internal DRAM and DMA can safely use them. So word-aligned HTTR. Heap caps malloc. Okay. You have DRAM is a memory that connects CPU data bus and use to hold data. Some kind of memory is this CPU instruction bus. If access to generic memory, all access. Okay, hold on. So this is direct, this is data random access memory. And then you have IRAM. Instruction. Instruction RAM. The DMA is only allowed to access internal DRAM. to ensure. And word aligned. Use the word aligned ATTR. Macro. So this is a macro apparently. So let me. Attribute. Oh, what the heck? Oh, this is a GCC. I don't even know what that is. Okay. This is a special GCC direct. That's really cool. Oh. Or you could use heaps. Heap caps malloc. Same as malloc. So you can also use free, okay. Full DMA safe. Okay. Use malloc cap DMA to allocate memory suitable. This one about malloc. Oh, ATTR stands for attribute. Attribute. So IRM attribute is the same. Keep malloc caps DMA. Okay, so you. Yeah, high school. So this is safe if you want to use it on the stack, but it's not as flexible, whereas using dynamic memory is more flexible than just using stack memory, to which you could just do you could just do okay, let's do this. Okay. So if we want to do it using instead of using stack memory and using heap char star, it's heaps caps aligned to alloc or aligned. Okay. The size, this will, so we wanted this 128. We want aligned. What's the thing on documentation? It's malloc cap DMA. Cap DMA. So this makes it DMA compatible, right? And then let's do char star Okay, I think that's it, right? Yeah. This makes it more DMA accessible. Oh shoot, what? Okay, I mean like oh, we need to free this. I need to free this. Hold on. Oh, I need to free as well. Heap caps free. let's try this. We have the free. We can't. Otherwise, that'll be a memory leak, which we obviously we don't want that. We also have to do this. It's a pointer, right? Okay, good. Yeah, we're supposed to free. Oh shoot, what's that? Let me see that. Okay. Supposedly you're supposed to free outside of the loop, not inside of the loop. That makes sense because you're not freeing every time. You have to free only once. Otherwise you're freeing more than you need to. Okay, good. All right. Okay. Okay. All right, so perfect. We got it working. So this is how SPI is used. Okay. It's like a feedback loop for SPI. Use DMA. So use DMA here. And then you transmit and receive heaps cap. You free the dynamically allocated memory, and then okay, you copy. Okay, sorry about that. Okay, was there anything else to do? Okay, we understand SPI. I think, yeah, I mean, like, and DMA too. So, receive buffer, and then transmit the data between ESO and Mossy. Slave, between master and slave. So the way the data transfer the fact that you can transfer the data easily by just accessing the memory without needing the CPU is the practical utility of DMA here. So okay, that's perfect. fantastic. Okay. SPI and DMA all in one video, which is great. Oh. I think tomorrow I might do UR and then we'll do I squared C. And then we can start a project, maybe. Is there really anything else to cover here? Like, I mean, like, theory-wise, like, let's go back to the roadmap. Okay, let's go back to the roadmap. Okay. So we got, JTAG, that's definitely worth learning. JTAG. OS stuff and Linux kernel. This is definitely something we should cover sometime in the future. I don't know, like, too much right now, but it's definitely worth doing that. Agile and Scrum, that's like project management stuff. I used that for like, for like a course a long time ago. Okay, so JTAG. And then what's clock management here? Clock management. An oscillator clock. Alright, get rid of that. %99 of developers don't get sockets. That's crazy.
So today I'm bringing you a video on how to change the clock frequency on the STM.
Okay, this is some clock management. Clock management in the ESP32. No, sorry. So, okay. So yeah, tomorrow we can do UR and we can do I squared C. I mean, I don't even think, is it really worth learning that? I mean, it's worth, if you know conceptual what UR does. Like, UR on ESP32.
This box. Up to 5.
Oh wow.
AM increment.
Well, this is why I say get an eye on cable. It's optional, it's there. You want to do a bit more than just using it as Wi-Fi. So you have another expectation of installed with them. You're good to watch out for when you're using these type of protocols as well to make sure that you don't maintain the same voltage line. As well, while we're here, we can look at the extra things that we're surrounding. And it seems like other things wrong here. Right to send and clean. So that's the one thing. Don't worry, everything to see. So you do have these extra things. I don't and whilst we're on here, I will take a look at the SARs so we can see that we have this one. And this is the SARs. We have this one. And I'll have a look. To pass along. And what we're going to do here is look at how we've actually went about doing this. So we've included all the main file
maybe really you are DSP32 documentation. This is 5.4.1. Okay. Setting baud rate, assigning pins for connections to device, use interrupts, run UART communication, install drivers. Okay. Alright, sorry about that. Anyway, let's move to the you receive data or use interrupts. Use interrupts. Use microcontrollers. Okay, so yeah, okay. Okay. All right. 1 second.
What?
Oh, stop.
Let's.
Nope. Okay. Alright, I think I'm gonna end it here. Yeah, okay. Alright, thank you. Oh my god, it happens again. Alright. Microphone always falling. Alright, thank you guys for watching this video. Today we covered SPI and DMA. Tomorrow we might cover UR and I2C. So yeah, thank you guys for watching and have a great day.